able to introduce my advisor and BIDMaP member, Gerbrand Ceder. He actually rejoined us. He is originally a Berkeley alum. He got his PhD in Berkeley and then afterwards started his faculty career at MIT before coming back in the early 2010s. So Gerbrand Ceder is a Samsung Distinguished Professor at UC Berkeley, and he's also a senior faculty scientist at LBL. His publication numbers, just by the resume, are really impressive. He has 160,000 citations, a Hirsch index of 190, and 50 US patents. Also impressive are his memberships in different organizations, including the National Academy of Engineering in the US, Royal Flemish Academy, Belgium Academy for Science and the Arts, American Academy of Arts and Sciences. And then, of course, he leads a lot of different endeavors throughout the scientific community, including being a co-founder of Radical.AI. He is the leader of the Department of Energy program in earth climate cathodes, doing materials genome initiative, for instance. But I think especially as a postdoc, as a student, as a researcher in his group, probably the most important thing and impressive thing about Gerbrand is his ability to talk about science deeply, talk about a lot of different knowledge deeply. So, being able to talk about characterization and AI, even Yosemite hiking trails, as well as patisserie. So with that, turn the floor over to you.
Great, thanks, Laura. Certainly one of the more fun introductions I've gotten, but thank you. One thing about my career is that you probably don't know, but I started life as a metallurgist. I was actually trained as a metallurgist and mining person. And the reason I came to Berkeley to do metallurgy was so empirical at the time that I was so frustrated by doing experiments. I go like, none of this ever works. You never know what you're doing. It's just all empirical, and the machines always break. I was really frustrated by the machines always breaking. So I said, I don't want to do this anymore. I want to do a PhD in theory, which is theory of materials was very new at the time. And there were only a few groups that did that in a material science concept. And one, the ones was here in Berkeley, was the Fontaine group, who's passed away now. So I came into theory here, and now, I don't know how many years later, we're kind of back mostly doing experiments, but maybe somewhat more intelligent than the metallurgy from 40 years ago. But you're going to see at the end of the talk, I'll show you something about what we do at Radical, which is the startup I'm involved, which is back to metallurgy, so full circles. The slides I have are from a talk I gave just 2 days ago at the GRC, the Gordon Research Conference on AI in material science, which I highly recommend. It's sadly only held every 2 years, but one of the best conferences I've been to in a really long time. They may not be fully adjusted for this audience, so we can make it informal as a presentation, so you're welcome to interrupt and ask questions. Okay, so I wanted to give a little bit of history. Some of it is personal, some of it is related to initiatives you're familiar with. In 2003, I was still at MIT, and a bunch of us sat around, and we had just kind of started the very beginning of high-throughput density functional theory. Basically, through the 90s, density function had sort of stabilized as a method. The algorithms were becoming stable. In the old days, you had to sit there and fine-tune the optimization schemes and the K-point integrations and literally stare at the convergence to make it happen. And what happened sort of in the 90s that people started building stable algorithms and codes. So at that time, we realized, well, if you do one calculation, you can do hundreds and thousands of them. And at one point, I sat around. I was very frustrated that we kept on doing many density functional theory calculations, and Dane Morgan and I talked at some point that why are we always starting from scratch? Why do we always solve the Schrödinger equation hundreds and thousands of times, acting like we've never learned anything? And so came the idea of what we would call machine learning. Now, at the time, it was actually called statistical learning. The term machine learning appeared much later, sort of in the science field. And we did this paper, which, if you're sort of familiar, the cast of characters here is pretty well known. There's Christine, who leads the materials project now. There's Stefano Cortarola, who later went on to start a really big database, HFlow, at Duke. Dane Morgan, who did high-throughput computing and still does on defects in materials at University of Wisconsin now. John Rogers, you probably don't know, but John Rogers was one of the first people who built a very large database of intermetallic structures. And the idea of this paper was that what we showed in this paper is that if you did a small amount of DFT calculations on the intermetallic crystal structures that you could actually fairly accurately predict these structures in other compounds. So without actually doing the DFT calculations. We certainly did not understand at that time the concept of MLPs and stuff like that was completely unknown to us, but it was sort of extrapolation of known calculations. And a few years later, I got drafted to an initiative at MIT, which was called the Energy Initiative. Clean tech and clean energy was getting very hot then, and MIT decided they wanted to do an energy initiative. I was extremely bored in many of the meetings, and I doodled on things, and at some point I put a white paper together, and with this idea that computing is fully scalable. It's now about mid-2006, 2007, and we made the statement that scanning most of the inorganic world is within reach, which was a bold statement at the time, but the point was that, and you could do thousands of DFT calculations, or we started to show that, and the world of inorganic chemistry is actually not that large. At the time, there were about 100,000 known inorganic compounds. The world of inorganic compounds is actually much smaller than the world of organic chemistry. People can argue about how many compounds there might be as possibilities, but the known world was about 100,000. And so we made the statement that you could actually probably scan most of them or scan part of them, and then through what we call data mining at the time, actually make predictions about the other ones. And that led to what was then called the materials genome concept. The story is actually really that the materials project, which the beta version started at MIT, was actually called the materials genome project at the time. And we worked at one point with the Office of OSTP, the Office of Science and Technology Policy, to launch a nationwide materials initiative. And they wanted to call it the Materials Genome Initiative, but they said, well, then you can't use it anymore. So the Materials Genome Project became the Materials Project. And the Materials Genome became the Materials Genome Initiative at the time. So that's the sort of history of how we got into high throughput computing. This launched many software centers, and that actually then led to the Materials Project, which is one of the only few that's sort of standing still through that. Okay, that's a sort of a bit of history. So thinking now about how we used to think of computational screening at the time, we used to think about it sort of, we would define a very large set of compounds from which to screen. That could be the ICSD, but we could also like complement that with substituted compounds. So we would take known compounds and substitutions on them, and then we would successively screen through property. This is sort of the well-known screening funnel. So this has had some success. Today, people are sort of trying to do this with generative AI. But the question is, today, can you really do this in a single generative AI step? Because to do this in a single generative AI step, you would actually have to sort of know all models for actually all these properties. So there's a few challenges when you try to do this from sort of practical material science. And one is that it's challenging to find materials based on, actually, could I have a chair? I'm just a little, a little tired, sir. Thank you. So one challenge is that it's actually really hard to find materials based on novel mechanisms. And this is something we encountered, and I'm going to show you an example. So, in the mid-2000s, we got very excited that we could do high-throughput screening on materials. And we produced this scatter plot that we were very proud of at the time. We could do voltage versus capacity of cathode materials. And that actually led to some new materials, which are sort of shown in the middle here. These materials were completely unknown. They're sort of lithium metal carbonophosphates. There are actually none of these known in literature. They came out of high-throughput screening. We were very excited at the time. You could make them in all kinds of compositions and colors. And they actually worked in the battery. They were one of the first examples of truly computationally designed materials that you could actually also cycle. Well, that research was very exciting, but it got completely killed by something that happened by accident in his lab, is that we found lithium battery cathode materials that worked in contrast to what we thought. They were fully disordered materials. They were actually crystalline materials with disordered cathodes. And we never had expected this as a mechanism. And because we never expected this as a mechanism, we would actually have never included them in the screening, because when you screen for novel materials, you actually tend to include mechanisms that you understand. So now we had a new mechanism, and basically all old research died. We since then have spent 10 million of Department of Energy dollars completely focused on this new mechanism. And so this is an issue, right? When you do computational screening, you tend to look for materials based on ideas and concepts that you know. And if there is new phenomena that lead to certain properties, you tend to not include that, and so you need a certain amount of serendipity. The second thing is more sort of a comment I want to make to mostly sort of a theory crowd, is that compounds are not materials. Materials are complex arrangements of compounds, and steel is a good example of that. There are many phases in steel. And I'd like to bring up this example. It's an example that most of you encounter without knowing. One of the biggest advances in metallurgy was what's called trip steels. This stands for transformation-induced plasticity. These are used in crumple zones in cars and pillars. So they actually combine high yield strength with high ductility. So they can actually absorb an enormous amount of energy, and that's why they're used in crumple zones in cars. There's sort of no known compounds here. This was all about rearranging the microstructures and putting phases at their point where they easily transform, so that when you actually have an impact, a fresh impact, they absorb a lot of energy. The third practical point is that it is rare that when we work on a practical materials optimization, that there's only one property we care about. And this is what we tend to think about. If I make work on a battery material, we think of high energy density of the battery material. If I think of superconductivity, people think I need the highest TC. But in reality, what's actually really happens is that you're trying to optimize a property under a bunch of constraints, because there are other properties that are also required when you're trying to do an application. And I'll give you an example. If you look at the commercial application of high TC materials today, they are not the materials with the highest TC. They are materials with a somewhat lower than the highest TC, because they satisfy also a bunch of other requirements. And the issue you have if you do purely computational optimization is that unless you can deal with all these constraints properties or properties that act as constraints, it's very hard to do a purely computational optimization of a material. And the last challenge that I want to point out, I'm going to talk a little more about, is the synthesizability issue. What we are learning now, as we have gotten much better at predicting compounds, and we can do it in high throughput, that we have no theory for synthesizability. And that means we have no bound we can put on our space, the space in which we want to predict, to guarantee that these materials can actually be made. What often people in theory use is what's called energy above the hull. And energy above the hull is essentially a measure of competitiveness. Energy above the hull is essentially how much more energy do these materials cost compared to the competing phases. And Wenhao Sun and I, about 10 years ago, did a paper where we took the whole ICSD database of experimentally observed compounds, and then we used density functional theory to calculate what is the energy above the hull of materials that have been observed in nature. And this plot is often quoted, but then I'm going to show you another plot that's in the paper that nobody ever quotes, but it's just as important. So this plot is often quoted to say, well, this is actually showing in different chemistries the energy above the ground state that you observe. And I think this bar is like the 10th and the 90th percentile. And so what you see is kind of in general, by the time you hit 50 to 100 millielectron volts, so that's roughly 5 to 10 kilojoules per mole, you encompass most of the known metastabilities. Nitrites are unusual, and this is known in chemistry. Nitrites have very high metastability because of the triple bond on the nitrogen molecule. So if you just look at this plot, you would say, oh, if I predict things within 50 or 100 millielectron volt, it should be synthesizable. But that's where the mistake goes, because there's another plot in this paper, which I want to show. We took a lot of known chemistries. So these are materials that are very well known. Titanium oxide, zinc oxide, iron oxide. There are over 10,000 papers on TiO2, just to give you an idea. So what is shown in blue is the energy of the known metastable phases of these chemistries. And what you see is roughly, they also span about 50 to 100 millielectron volt, just like the previous one. But what's also shown is in red. In red is a bunch of virtual compounds we made up. And what you see, these have never been observed. And what you see is that they are also within that range of 0 to 100 MeV. So lowish energy, if that's a term, seems to be a necessary condition, but not a sufficient condition for synthesizability. And I think what's happening now as we do computational discovery of compounds, that we're basically discovering more and more of the red compounds. And our success rate in synthesis is actually going down considerably because we seem to be going into this space that I don't know if we can call it irrelevant, but that we have really zero synthetic success in. So I'm going to show you one more example. This is actually Lauren's work, I think from just before he joined BIDMaP. This is a compound that came out of the genome data set. A lot of you may be familiar with the data set that Google DeepMind released, claiming sort of millions of novel compounds. And it was sort of one chemistry in particular that caught our attention. Also, they had communicated to us that this was going to be a good sodium ion conductor. This is a sodium tin phosphate. So it can be any metal, but we use the one with tin. And we did calculations. We calculated this for a lot of substitutions on the metal. The tin one was of interest because they had predicted that to be a good conductor. It's only about 0.4 millielectron volt above the hull. So it's essentially almost on the hull. And I think it took Lauren, what, 6 months to synthesize or so. And the way this works is that in the first months, you have zero proof of existence. So this is not like organic chemistry where you see some product molecule as like 3%, and then you got to keep on refining. In some cases, we have zero signal. And you have to keep this in mind when we do AI. We're trying to optimize recipes where the signal is zero. But finally, she was able to make it. But then you look at other compounds, the hafnium one is actually on the hull, and we have had zero success in it. So we have no theory for synthesis in inorganic chemistry. And the problem is there's no massive equation here, right? There's no Schrödinger equation to solve to prove to come up with synthesizability. And it's also extremely hard to disprove synthesizability. It's essentially not possible.
Right, so that was my question. So maybe just Laura was not intelligent.
Yeah, no, this is fair, right? And
I know she's pretty intelligent, but
yeah, no, and this is a fair point that we cannot guarantee that there's no guarantee that these are non-synthesizable. But this is why we did this computational experiment, because this computational experiment is more like this is the community at large. I would argue that these red polymorphs of titanium oxide, that it's very unlikely that they would have never been observed. Right? There are sort of literally like 20 or 30 here. Even if we doubt Lauren, I think it's hard to doubt the community that they would have missed these polymorphs. So there seems to be a lot of low-lying energy states which have actually never been made, and there may be a reason for that because they are for some reason not synthesizable. So because of all these sort of complexities is why we wanted to build a lab and why we built it a few years ago. There were two reasons I wanted to build a lab. One was I wanted to accelerate synthesis so that we could have much faster answers. But the other one, I was sort of intrigued by having an AI playground in the physical world. I always thought of a lab a bit more as a testbed for AI. And I've always been interested in like how do you use AI to mimic scientific decision-making. And scientific decision-making first means that you can do AI-driven interpretation of data, right? There are 2 steps to make a lab autonomous. Well, there are 3. You have to automate the equipment, but the other one is you have to be able to do autonomous interpretation of data, which is something that humans have very often not really quantified. And then you have to do scientific decision-making, which humans have quantified even less. I'm constantly amazed how people make decisions iteratively in science in what seems to be an unorganized way. I have some result, I need to make it better. Can you explain to me your logic on what I do next? And in most cases, the answer is no. So that was the motivation for a lab. And this is now strange because normally I give this talk and you have not been to the lab. And I show a lot of videos and people are very impressed, but now you've actually been to the lab. So I'm not sure what to do with the videos. But I don't know, you may have learned a little bit about the history of A-Lab. A-Lab version 1.0 was made about, what is that now, 3 years ago, 3.5 years ago. by people like Bernardus and Yuqing and Yanzheng. Bernardus is here, right? There you go. Yeah, there you go. And it was actually a fairly compact lab. It was up at LBNL. It did precursor mixing, transfer to furnaces, and then one of the hardest parts, which was preparing samples for X-ray diffraction. One of the reasons that's so hard is that in an experimental lab, and I mean truly sort of experimental, where you do different things all the time, you don't know what you're going to get. And so one of the hardest challenges of the lab has been to deal with variable outcomes. I'll give you any example, like when we synthesize some material and we try to figure out a synthesis protocol, we get everything from powder in the crucible to some cake in the crucible that's caked on the crucible to nothing in the crucible because it all evaporates. And so dealing with these highly variable outcomes is actually one of the challenges in the lab. Okay, what you have seen here in Hearst Mining Building is what we call 2.0. And 2.0 was set up to have a lot more modularity. We wanted to expand, so we built a pod style lab where a mobile robot transferred between pods. We also wanted to broaden the base of materials that can be synthesized and include a lot more characterization and multimodal characterization. And I'll show you a few videos, and then we'll sort of get more into the science of how we try to stitch these things together. So hold on. Yeah.
So when you do an experiment, do you sometimes think, oh, I know to go to a synchrotron to sort of get an exact sort of high energy to actually analyze it or things like that? So does that ever happen, or is it always that just your 500,000 X-ray machine is good?
No, we do occasionally. So in fairness, we probably use the ALAP most as a lot of getting high amounts of data and sometimes getting enough data to do decision making. But yeah, we certainly take samples to the synchrotron. You just can't make it part of your fast autonomous loop, right?
So will your ALAP sort of flag it and put it into a little box and say to the undergrads, take it to the synchrotron tomorrow?
It's not that formalized, the process.
So it doesn't know that. Will not figure out that the instruments you have in the lab are not good enough. So does it just put this cake into the X-ray machine anyhow, even though the cake will probably not show anything, or what does it do? So
we have fidelity criteria on some of our decision making, right? So we can, on an X-ray spectrum, decide. So we don't know before we put it in, but after we take X-ray spectrum, we have criteria that tells us, first of all, the information about the quality of the information we get, the signal, but more importantly, we have confidence intervals on the decision making, on the interpretation of the spectrum, and that's where we wouldn't really take it to a synchrotron all the time because we don't go to the synchrotron like every week. I would say we use the very high quality data much more when we have a material pinpointed and we now want to learn more detailed structural information from it. So did they see the mobile robot, or okay, I can skip that then, even though it's cool to watch with. Okay. We enhanced the lab with the ability to deal with air sensitive materials where everything is in the glove box, and you probably saw that was quite effort. So everything's done in the glove box except X-ray diffraction, which we should have had. And there, Yuqing Fei, who's not here, who's actually still at the GRC, did sort of a first optimization campaign on ionic conductors. He optimized ionic conductors in what's called the inverse Spinel space. And you know, I want to show you how big this is. So he did 350 samples in 2 months. So everything was automated except the last step, which was the measurement of ionic conductivity, which because he could do it very fast, almost faster than the robot could do. And I don't think anybody has ever done 350 samples in that space together, and it was done here. We have now, and I'll show you a little bit of that, driven this lab in a purely agentic mode, where we actually can have agents decide how to operate the lab and how to analyze the data. We do ultra-fast heating. This is Pepe's work, where we have new techniques to do extreme fast heating, so we can get better stable phases in both the heating and in the cooling cycle. And then I think one of the sort of really key things that we're actually working on now, which is I think going to be very important on the synthesis, the way you learn synthesis by what's called in situ diffraction. So you basically stick a sample of a precursor into, traditionally was done in a beamline, and you actually take diffraction as the things start to react. So from that, you can actually learn the whole reaction paths and not what you find in papers. What you find in papers most of the time is actually, oh, I mix these things, I put it in a furnace, and this comes out. So within situ diffraction, you actually learn the whole reaction sequence. The problem is now that if you look at the literature, there's probably maybe 20, 30 in situ diffraction experiments done in all time overall the literature. So we've built here, we've automated in situ diffraction by working with Anton Parr. So this is actually where precursors will be loaded to a furnace. It's a little hard to see. I think I talked to it. Let me just quickly go back a little and speed it up. Oops. Because this will probably be one of the more important data sets that we produce. Yeah. So we're aiming to do probably around 5 or 6 a day, because when this robot can auto load the machine, we can actually do a typical run is probably sort of that order of sort of 4 or 5 hours. The challenge here was to load the furnace because it's a furnace in which the diffraction beam goes through, and to load the furnace with sample. So we're kind of basically ready to get this started at this point. Okay, I'm going to show you a few examples and also, increase the level of complexity of what you can do now. So one thing you can do is you can now think of a lab and organizing workflows, the way you set up computation in work. It's a little more challenging, but you can, in principle, build, paths through the lab, and you can actually have decision-making points that modify that path through the lab, just like a computation workflow. Here's an example that Bernard Desrendi has done on single phase high entropy nasacons. This is sort of an interesting idea that was published in Science a few years ago by Yan Zheng, that if you take what's called nasacon materials, these are typically lithium or sodium metal phosphates, and you can put silicate groups in there, that if you measure their conductivity with a single metal in here, so here's, for example, a lithium one with either hafnium or tin or titanium or zirconium, this is the conductivity, that if you actually mix them all together, you get a synergistic effect, which is called a high entropy effect. So when you mix them together, you get much better conductivity than each of the metals by themselves. And this is sort of repeatable across chemistries. This is true for the sodium nasacons, but these are actually not a totally different crystal structure. These are what's called garnets. And again, what you see is if you have small here is binary combinations, but if you sort of mix these binary combinations into a ternary or a quaternary, you get again higher conductivity than the actual elements themselves. And this is kind of understood where this comes from. So we were trying to sort of optimize single phase nasacons in a kind of this isn't quite really a sort of a purely agentic way to drive a lab. It's a way to sort of drive the lab with various cost functions that are actually pulling against each other. So we want high conductivity, right? So we have a semi-predictive model for sodium ion conductivity. Now, in principle, you could inline do molecular dynamics, do sodium ion conductivity, but we don't do that yet because it's sort of somewhat time-consuming and complexity. So we have a literature extracted, so you could say a machine learned model, a very simple model that's based on ionic sizes and sodium ion content. And this comes from literature data that we've actually just mined and built a simple model around. So this is a static model. You can calculate energies above the hull if you want to learn about synthesizability. But again, we don't want to do that. We don't really want to do yet inline computation, although it's an interesting sort of thing to do in the future. So again, we use, this is the model of Jianyang Wang, who looked at a lot of nasacons and figured out somewhat about the energetics of them. So this is almost like a PCA style model for getting synthesizability. And these are static models. But then we use dynamic models, and these are basically, you could almost think of them as in context models, where you start to learn from the data you have generated in the lab. For example, if we try synthesis and we see impurity phases, we kind of know to stay away from some of those elements. And the way the model is implemented is a little more complicated. So this is how the lab sort of updates its information. And I'm going to show you what this means. If I want to say make a nasicon with 3 primary elements, there are more elements, but say these are 3 metals, you have some target, maybe that's from optimizing conductivity, but in reality, that's not what you'll get. You won't get single phase unless you're really lucky in your first try. When you do experimental synthesis, you always get some phase mixture. You'll get like sort of 3 points in this phase space that combine to that composition. And what you really need to do first, if you want to do a reliable conductivity measure, you need to make a single phase nasicon, so you know what you're measuring conductivity on. So what you really need to do is sort of build compositional change vectors that iterate rapidly to single phase. And here's sort of an example. I think Bernardus was trying to target this nasicon with equal amounts of zirconium, tin, and germanium. And this is the diffraction pattern comes out. It's extremely messy. If you try to fit it with a single phase nasicon, you get a lot of, these are typically different squats between the measured and the actual hypothesized composition. And so what the diffraction algorithm has to do is has to figure out not just what the target phase is and when you have it, but what the impurity phase is. And this is what's typically not done in experiments. Most people, when they do experiments, they kind of try to make something and they see if they have a single phase, it's great. If they don't, they try something else. But very rarely do people characterize fully their failed experiments. And because of that, we lose a lot of important information. So we also try to characterize, I don't like to call them failed experiments. They're sort of experiments that didn't do what we wanted them to do, but they still provide information. So for example, here, the analysis will tell you, and I'll show you in a second how we do this, that we have sodium germanium phosphate. So you can already kind of think what the algorithm is going to do, right? It's going to reduce the germanium content because that's how you have, will get less impurity phase. And so you iterate, and the lab can do this by itself. And after about sort of 4 trials, you start to get a single phase nasicon with a lot less impurity. So what the lab can basically do now is it can iterate mostly by itself from some starting point in phase space to a single phase compound without the human intervention. And there's some more examples of this here. And this has actually led us to now, when we bring in the cost function, so in the beginning, we actually only included the synthesizability function, but when we now bring in the cost function to also optimize conductivity, we can actually get to, and I masked the compositions on an older slide. I don't think I have to hide it anymore. So we can actually get the nasicons now with very good conductivity. This is among the highest bulk conductivities of known sodium nasicons. So
question. Yeah. So before you mentioned that typically people do this experiment if they get the mixture just throw it out into something else. That indicates that they're really there. Is it just because they know that would be bad in the spatial optimization which your ADAM is put in, or do they just not try?
Most people don't do Bayesian optimization. Most people who do experiments do it, the iteration from beginning to success is extremely non-quantitative in the real world. People sort of look at something, saying this is good, this is bad. I don't know what units good and bad are, but and then magically decide to do something else. And that magic sometimes works, but our point is that if you want to build rational decision-making algorithms to do iterative science, you have to quantify what you have.
So you're saying it's not only that your A-lab is much better in this data refinement, but actually the humans will have no idea how to do it.
I think that I'll show an example. I don't think they will do it as good as the AI does. I'll show an example at the end where we tested human against the machine. But I think that they don't even, we see a lot of data where the failures are not even quantified. They're just classified as failures. And it's by quantifying them, I feel that you can build up the knowledge of how to get faster to the end results.
So they just don't have this image in the head of a phase mixture and let's try to refine it to get to the pure point in the middle. They just say mixture equals failure. I just don't even want to know why it failed. Is that
may be a simplification, but basically it is that, yes. We see a lot of I work in the battery space. Oh, I tried something, it's a bad battery material, let me move on and try something else. And it's very hard to quantify how good that process is. I guess maybe
for really good chemists, that process actually works really well because they often have intuitive knowledge. But I think for most of us, that process doesn't work particularly well. Okay, let me skip this. So I wanted to have a few slides on making decisions when you have messy and noisy data, because, you know, my experience is that whenever we make a model and we train it on model data, and, you know, we do the classic things, we leave out test sets that we then later test. And when I take that algorithm, which performed that supposedly really well, and then I take it out in the wild, as I call it, on the real experiment, it never performs as well. And that may have things to do with the fact that our sets or models that we train algorithms on are probably always simpler than the real world. They may have hidden correlations that we're not aware of. And then the fact is that noise is in the real world probably a little more unpredictable. So I'm going to show you an example, and it's an example that we worked on for a long time, I think finally solved, which is on X-ray diffraction. So powder X-ray diffraction is probably the most common technique to detect what's going on in phases. You know, it gives you some kind of, it's essentially the spectrum, for those of you not familiar, is really a Fourier transform of the crystal structure, squared and then spherically integrated, right? So that's why you see actually an angle. So you only lose information even in theory because you square the Fourier transform, so you lose phase information, then you spherically integrate, so you lose a little more information. But in reality, you use a lot more because there's peak broadening going on. There could be preferred orientations that your powders actually are not isotropically distributed. Some phases that are references may not be exactly what you have. There may be sort of solutions of other elements in there. So you kind of have to do interpretations in this sort of very noisy environment. And the classic way that that's done is that people take a database of phases and basically try to fit their diffraction pattern to what you have in the experiment. And quality of fit is typically measured by some kind of root mean square difference in intensity or something like that. And so I'm going to show an example how bad that can be. And that'll show you why nobody ever sees this. So here we were trying to make sodium vanadium oxide, and we were trying to make it from V2O5 and sodium carbonate and carbon. The carbon is there for to do reduction. And if you do a mathematical optimization of this diffraction sample, it tells you that there's V2O3, which is very reasonable because this is vanadium 5 plus, this is vanadium 3 plus, you've probably done reduction. And then it also says there's 40% of frozen carbon monoxide. Highly unlikely, right? We'd also be dead if that were there, but you know, there is no frozen carbon monoxide at normal conditions. But you know, a simple fitting algorithm doesn't know that, right? Because it's in the database, therefore I should fit it. So why is this never seen by humans? Because humans never tried this. So when humans try to fit the diffraction pattern, they have preconditioned in. They go what they think is reasonable. And I gotta say, very often it's what they think the answer should be. So human bias can be both good and bad, right? It makes you take out the crazy solutions, but it also means sometimes that you miss things. So the way we have solved that is by a dual approach. One is what's called DARA, which is that rather than a single solution, we actually generate a tree of possible solutions. So we actually do a tree search, and we take all the top solutions with a certain fit score. But that's not enough, because what I'll show you, what I showed you before, the top mathematical fit is usually not the right one. So then we use what we call AIF, an augmented interpretation framework, which was mostly developed by Olympia Darcy and by Jane at the lab, and that will then re-rank the solution. And this is essentially what you're going to see is it gives them a chemical prior information. So it does that in a simple Bayesian way that, you know, the probability that a certain interpretation on the data is correct is now interpreted with a prior. So you can now give a certain chemical prior to particular information, and this is where you can put in your chemical intuition, your heuristics, or whatever. Well, the way we do it, I'll show in a second. So the first term in the Bayesian expansion is essentially a fit, right? This is the probability that the data can be reproduced given the information. So that's typically like a fit. So we measure like RWP, least squares fit, or missing peaks. This is all very well known. The second piece is what's less known. How do you mathematically put in a prior? So we've thought of a lot of things to do that. What we use today is the answer from an LLM, and then also a more mathematical term, which is a composition balance, whether the things you find in the fraction pattern or claim to find can make up the overall composition of the sample. Let me show you sort of how that works. Here's a synthesis of calcium vanadates, which we did with calcium carbonate and vanadium oxide in argon and hydrogen, because we want to be reducing. Again, if you take the score with the best mathematical fit, it tells you that you have these two phases. So this interpretation here has the best mathematical score. It tells you there's calcium vanadium oxide and calcium carbide. Calcium carbide is extremely unlikely, because if I could take calcium carbonate and if it'd be that easy to reduce it to calcium carbide, I'd probably have a solution to the CO2 problem in the world. So very unlikely. So if you now actually start using the chemical priors, it actually re-ranks them, and it actually takes this to be the most probable solution. And this is a much more likely solution, actually. And if you do careful analysis, you find that this is actually the solution. But what I want to show you is how it does that. Where do the weights come from to reanalyze this? If you actually look at how it gets reweighted, so this is actually the weight of the different metrics in the ultimate score. And when you see the RWP is the mathematical fit, right, is the highest for interpretation 1 because it's the best mathematical one. But what you see is what is really making a difference is the LLM. So basically the answers from the LLM here are dominant in giving it the right interpretation. What I found interesting is that if you ask the LLM for the explanation, this is what it gives you. And if you actually are a chemist and you read this carefully, this is sort of okay, but actually not really correct. Because it says calcium carbide is highly unlikely to form under these conditions due to the presence of oxygen in the atmosphere, which there is not. I mean, there is oxygen in the calcium carbonate precursor, but there's really no oxygen in the atmosphere. So it kind of gets the right answer, but the decoder here hasn't really done its job giving an explanation, I would say, that is rigorously correct. I mean, if a student gives this to me on a prelim exam, I wouldn't fail them, but I certainly wouldn't give them a passing score, because it's sort of the right answer, but the logic is slightly lost. Okay. How much time do I have?
7 minutes.
Okay. And I'm sorry, Andrea, I'm gonna skip your part on the automated SE. Okay. So I'll be brief here, and now I want to show you some stuff that Radical did. So what we have now also started to do, and this is Hugh's work, who's here, is whether we can have actually full agentic access to ALab, because agentic AI is really popular, and I think it's showing tremendous promise that you can, essentially have agents without training, essentially can be self-learning and self-reflecting. And there's been a lot of demonstrations of that shown that you can have agents that can figure out what software to call, operate the software, learn from it, and get answers from it. And we've certainly done quite a bit of that. So we wanted to see if the same was true with the lab. So Hugh here tested if an agent can actually figure out how to run a lab without actually us explicitly telling it. And so we gave it this task to interact with the A-Lab OS. We had to tell it a little bit about it and where to find documentation. And we wanted it to make this compound. This is actually one of the inverse spinels. And this is actually the prompt. We had to give it a little more information, but it sort of tells us a little bit operational issues, use for mixing balls and all this kind of stuff. But we don't tell it actually how to interact with the system. Right? We don't tell it how to, we don't tell it how to run the API or anything like that. And after a few attempts, this actually works. This actually made this material. I'll skip this. This is actually the diffraction pattern. It's actually almost phase pure, almost completely phase pure. And we can actually also have the agent figure out how to interpret the data, because we want to measure the ionic conductivity of this material. And ionic conductivity doesn't kind of come out as a number. Ionic conductivity is actually an impedance spectrum, and then the impedance spectrum has to be fitted and interpreted. And so all this can be done agentically. And I think this is sort of a hint, maybe a sort of small example of a hint of what the future of science will look like, in my opinion. So the last thing I want to show you is radically different, no pun intended, but I'm involved with a startup that's actually in New York, Radical.AI, who works that works completely different space, the very high temperature metal space. So these are metals that are for extreme high temperature applications, like over 2000 degrees, which is where almost nothing survives. This is mostly for things that go in and out of space, right? Re-entry issues. So heating, when you do re-entry in the atmosphere, heating, of course, by friction against the atmosphere is the biggest challenge. And they built an autonomous lab in less than a year that does metal. I think if you never change the parts melting, it come back. This is about what you're seeing here is probably about 2,500, 3,000 degrees. It'll come back. This is done by really an electrical arc that just keeps on transferring heat to the sample. This is a metal wave basis. This is accelerated. This actually node has some sensors with different metals. This is deflecting, and this is actually a hardness tester. So the first thing we do is also exactly measure how hard it's going to be. But I think what you guys may be more interested in, this team has set up a full agentic approach to control the lab and to do materials optimization. So the system consists essentially of a bunch of LLMs that are specialized to take certain tasks. There's sort of an Uber LLM, and then there's Claude that does code generation for the team. So the agent can search through papers. So the company has several million papers that it paid for, sadly, through Elsevier and all these other shenanigans. It can run thermocalc, which is known thermodynamic software to get melting points of materials, to get phasing of materials. It actually runs atomistic simulations as well, so it can take full control of atomistic simulations. And it essentially typically runs about 50 agents at the same time to do optimization. And I gotta say, I was skeptical about this, even though I'm a co-founder of the company. So at one point I asked him, can we do a test of human against the machine? And we truly did. I'm going to show you the result. So first I'm going to show you zero shot. So everybody was given the same information. And this is a zero shot approach. And what we're plotting here is hardness. And so we want to maximize that. And this is a numerical rating of oxidation resistance, but low number is good here. Just low number is good because the rating is actually given by humans because this is a re-entry application. So what you do is you stick a sample in a furnace at 1500 Celsius, you expose it to oxygen, and you see how the sample comes out. Most samples just fall apart. They're like totally, embrittle, they evaporate, whatever. One means that sample has kept what's called a protective scale. So some metals keep an oxide, and that prevents them from further oxidation. This is the human, orange. It was actually two humans collaborating. Blue is the agentic system, zero shot approach. And now you could argue maybe the humans were not good enough, right? And the humans are people with a PhD in this is high-entropy alloys. Both of them have a PhD in that field, and they've been out they're still young. They've been out for about 2-3 years. But I agree, it's very hard to do the experiment like, could we beat all humans? Maybe not. In my opinion, that's not the point. I think I want to beat the average human because I always don't have the best human available. But I'm going to show you on something. So what if you go away? What if you now start doing in-context learning? So here's another agentic campaign. Here, the agent was asked to maintain hardness, but improve oxidation resistance because we were given that challenge by the Air Force. So this is zero shot, this part. It's kind of like, it's not really randomly sampling space, right? Because it has information. And then it starts to do in-context learning. This is the mass change in oxidation. You want to keep that low because mass change comes from if you oxidize, you pick up mass, right? Your mass increases, or it can be negative if you volatilize things. And so what you see is that basically, as soon as it starts doing in-context learning, it gets really good, right? It slowly iterates down to very low mass gain. And the result I'm going to show you, a real material, is actually a material that has extremely good oxidation resistance at high temperature. So I've become convinced. So here's an example. This is the radical alloy that's exposed at 1500 Celsius for 30 minutes. This is before, this is after. The side, except for being a bit blackened, it's exactly the same. This is what's called CO13, it's a commercial alloy. In fairness, probably not really designed for these super high oxidation conditions, but it's designed for operation about 1350 degrees Celsius. We expose to 1500, completely falls apart. It's like basically powder. And this is hard to see. I need a better picture. The way that reentry is simulated, because you can't really do the test, the real test easily, right? Is that you take a piece of metal like a plaque and you put a blowtorch in front of it, and you basically just fire the blowtorch for a long time, because a blowtorch can go to very high temperature, multiple thousand degrees. It can have any atmosphere you want it to be. It can be reducing, it can be oxidizing, and it also has certain abrasive effects, just like the atmosphere. And this you can't see, but this is the commercial. This has an etch pit in it where the blowtorch is, and this is the alloy that came out of the agentic decision campaign. And since then, data that surprised me, I'm going to show you. This is how the lab is run today at Radical. This is experiments put in by a human in orange. Blue is by agents. So the agents are completely running the lab now. And, you know, this is kind of remarkable because if you were to meet the material science guys, they're pretty conservative. Like they never thought the agents would do better, but they've kind of given up their position to the agents, basically. The agents are basically orchestrating most of the experiments in the lab today. So, and this is where we are. I think we're the only real chemistry lab in Manhattan. Soon to move to Brooklyn. So anyway, I'll I'll end here. And the conclusion, this were my GRC conclusions, but I think I don't need to convince you about the importance of AIs. Thank you. And the whole team, sorry. Many of them who are here.
I think we can take some questions for Garrett. Anyone has any?
So, thank you, Professor, for the great talk. I'm a graduate student from Professor Mayagi's group, and I have a question for that. The slide where you talk about the data for PXRD analysis. So you show that you added the LM predicted probabilities. I'm wondering, like, how these probabilities are predicted by LM. I mean, mathematically, because they're not unlike the RWP where they have a mathematical formula. And how these LM predicted probabilities are calibrated. I mean,
Okay,
are they reliable? And
so we simply ask the LLM how likely a certain interpretations or how likely certain phases are to exist under certain reaction conditions.
The way the calibration is done is
what actually shows up in the Bayesian probability is some weighted score from, in our case, only two terms, the LLM output and then the composition score. And the weights we train on a data set, I think we have a data set that's been expert evaluated that I forgot if it was 50 or 100. And so we train the weights so they reproduce that. Does that make sense?
thank you.
I can maybe ask a question. Especially when you think about like the landscape of the material science startup changing, right? We've got like periodic, radical, all these. How far do you think that radical needs to go in terms of things like, I don't know, high temperature oxidation scale? Because as far as I understand it, one of the big problems with scale formation is like mechanical properties, but mechanical properties of the scale, peeling off, things like this. Like how far do big A labs go for property testing?
That's a good question. So one of the major investors in Radical is RTX, Raytheon, right? And we have been told multiple times that we don't have that if we come up with a good alloy suggestion, they'll be happy to take it over. Having said that, I don't think every customer will be as easygoing. I think the reason they have that statement because this is such a novel, unexplored space that they're just looking for any good idea in that space. It's also such an extremely challenging space, the high temperature space. But I'm sure that if you go to, I don't know, somebody who needs a new piece of titanium or aluminum metal, I think their demands will probably be closer to the product. So Radical is expanding what it's building to do high temperature mechanical testing, which is challenging, right? Because you're building basic equipment that can test metals at line. 2000 degrees. And for those of you who are into material science and metallurgy, first of all, there's not a lot of metals that you can build all stuff from, right? To do 2000 degree testing, and same with operating equipment like that. But it can be done. But I think the trick is to learn as much as possible from easier tests. There are also models that are reasonably good at extrapolating low temperature behavior to high temperatures. So what I like about the sort of agentic approach is that it is completely straightforward to mix computer and experimental data. They are just signals, right? They're signals into your agentic system. They don't even need to be super accurate as long as they have signal value. So for example, we don't measure the melting point of our alloys today, we calculate it. That calculation is not super accurate, but it's still, it has signal value. And you could almost, you almost think that the agent just treats it as a signal. It doesn't treat it as this is the melting point. And so it probably at some point even learns the difference between the real number and actually the calculated number. So even with models that are not 100% rigorous, you can send your optimization in the right direction. And then you just measure it in the end, right?
How creative are these compositions or materials that the AI?
It's a good question. I couldn't jump to you, but the agent had actually more chemical diversity than the humans.
Okay.
Yeah. I actually think it's the humans who have less chemical diversity. They seem to have picked more, and that's maybe why they missed, right? They seem to have picked more things along what they knew.
But like at the end, when you see the solution, is it a, oh wow, I would have never thought about this, or it's, oh, it makes sense?
You know, so the AGA space is about 6-7 components, right? Roughly. You know, there's certainly aspects of it that make sense, right? So people in general know, well, if you add these elements, the oxide scale gets better. If you add these elements, the oxide scale gets worse. But the problem is that that information rapidly becomes not very useful when you try to do a constrained optimization, right? Because we all know, oh, if I want some perfect oxidation result, I lose all of niobium and tantalum, but then I lose other properties. So doing that careful trade-off is really, I think, what you need the guy for. Yeah, if you just tell me, I just care about one property, you don't need an optimization system.
One logistic question, all of the paper you're paying for, are they all alloy or metal papers, or like what's the composition? Are they high entropy?
No. We have so I don't want to be 100% agrees with the publishers, but they have essentially access to almost all of the library of the publishers. What they do then is that they do a first order index of them, right? So that you don't always have to search through 5 million papers. But then, unlike what you see in some other systems, so what some other systems do is that what I've seen some systems do is that they index them, and then they use that index to put a certain amount of papers in context. But with an LM, you can't put like 10,000 papers in context, right? So it becomes crazy. So the way Radical does it, that it actually uses the index to find a lot of papers, and it takes snippets out of them, and those go in context, but not the whole papers. And that seems to work much more effectively. But we have millions of papers. It's insane though when you have to pay the publishers. It's really insane. But what are you going to do? And we've already paid for it once, right?
All right, so I think with that, we'll give Garrett another round of applause. Thank you.
Thank you.
I had like 50.
Oh, really?
I think that we cleared our throughput metrics.
I see.
How full
Yeah.
was the visit?
Yeah, I think we had about 60.
Okay, so people didn't register, but then a lot.
I see. They just show up. That's okay.
Just wanted to say, I don't think we.
Oh,
Chemistry.
you know, I know your name.
Catalysis lead, I know, so I hear your name.
I've heard your name all the time, but I do think we never met actually.